So our topic is on flange bolt coupling. So in any shaft connection called flange bolt coupling as shown in the figure, so we have here the illustration for a shaft connection. So that shaft connection is being called as flange bolt coupling. So there is a torque being transmitted by the shearing force P created in the bolt that is assumed to be uniformly distributed. So bolt coupling is a connection between two shafts, and this coupling is a mechanical element part that connects two shafts together to accurately transmit the power. So in other words, our shaft coupling that is used for power and torque transmission between two rotating shafts. An example for the shaft, we have the motors and pumps, compressors, and generators. So there is a torque which is transmitted by the shearing force P, and that shearing force P is being created in the bolt. So we have here the illustration. So we have here a bolt. So it creates a shearing force P, which is equivalent to area times our tau, which has the shearing force. And that can be equivalent to pi d squared all over 4 times tau over pi d squared all over 4 is the area of our bolt. And this shearing force P is assumed to be uniformly distributed. So for any number of bolts and the torque capacity of the coupling is, we have our T to represents torque capacity, which is equal to P times R times N. And of course, if we try to substitute the value for P, that can be equal to pi d squared all over 4 times tau times R times N. So this is applicable to one concentric row of bolts. However, this is an illustration for one concentric rows of bolts. However, if there will be two concentric rows of bolt, the torque capacity will be equivalent to T, which is equal to P sub 1, R sub 1, N sub 1 plus P sub 2, R sub 2 times N sub 2. And this is an illustration for two concentric rows of bolts. So we have an outer circle and we have the inner circle. So our 1 is a subscript 2 represents for the outer circle, and 2 is the subscript to represent for the inner circle. Of course, on the outer circle and in the inner circle, we have bolts, and it creates also a shearing forces. So that is denoted by P sub 1 for the outer concentric rows of bolts, and we have P sub 2 to represent the shearing force on the inner circle of bolts. For rigid flanges, the shear deformations in the bolts are proportional to the radial distances from the shaft axis. So therefore, the shear strains are related by this expression. So the shear deformation are proportional to the radial distances, and we can express that through this mathematically, that deformation over radial distances for the outer concentric rows of bolts to the inner concentric rows of bolts. And using the Hooke's law for shear, we can have the equation that modulus of rigidity, denoted by G, is equal to tau all over gamma, and that will be equivalent to this expression. So if we're going to have this is an expression for our outer circle equal to the inner circle, or this is in terms of the shearing stresses with respect to the modulus of rigidity and the radial distances, or that can also be expressed to this expression or this equation. This is now in terms of we have just substituted the value for our tau, for our stress, which is force all over area. However, if the bolts on the two circles have the same area, meaning to say area 1 is equal to area 2, and if the bolts are made of the same material, wherein G1 is equal to G2, the relation between P1 and P2 can be reduced into this equation. So this expression was reduced into this expression since we have the same area, we have the same material, so G1 equal to G2 and A1 is equal to A2. So we can have now this mathematical expression, the relationship now between the force and the radial distances for our outer circle and the inner circle. So our first a flange bolt coupling consists of 10 20 mm diameter bolts spaced evenly around a bolt circle 400 mm in diameter. Determine the torque capacity of the coupling if the allowable shearing stress in the bolt is 40 megapascal. So we have here our illustration for our problem number 1. So this we only have one concentric rows of bolt, and the bolts has a diameter of 20 mm, and it has bolt circle which is the spaced is 200 mm. So that is the actually we have here the illustration for the one concentric rows of bolts. Of course, we have our torque and denoted by our T. So we have our torque denoted by our T, and of course we have our shearing force, which is denoted by our P. So those are the shearing forces that is acting on our bolt. So for this example, we simply have our equation, which is equivalent to T is equal to P times R times N. So if we're going to make use of this equation, so this one can be equivalent to area times tau multiplied to R times N. So if we try to have the value, so we have pi d squared all over 4 times tau times R times N. So therefore, if we try to substitute the values here for the diameter, we have our tau, which is our allowable shearing stress, which is 40, and our r, which is the radius, which is 200. So this is our r. So our n is the number of bolts. We have 10 number of bolts. So therefore, we have pi times 20 raised to the second all over 4 times our allowable shearing stress, which is 40 megapascal, times our r, which is our radius, 200 mm, times the number of bolts. We have 10 bolts, so therefore, if we try to simplify this one, this can be equivalent to 8 million pi Newton meters, or this can be equivalent, actually, if we try to simplify this one, we can have the value of 25.13 in kilonewton meter. So that is for our example number 1. For our example number 2, we have here the problem, which has a flange bolt coupling consists of 8 10 mm diameter steel bolt on a bolt circle, which has 400 mm in diameter, and 6 10 mm diameter steel bolt on the concentric row circle, which has 300 mm in diameter, as shown in our figure. What torque can be applied without exceeding a shearing stress of 60 megapascal in the bolt? So for this illustration, for this problem rather, we're given with two concentric rows of bolts. So we have here our illustration, our figure. So it has a radius of 200 mm and one for the outer circle, and the inner circle is 150 mm. So we have here P1 to represent our for our outer circle, and P sub 2 for the shearing force on the inner circle. So for this problem, if we're going to have our solution, we're going to start with the force acting on one bolt in the outer circle. So we're going to have for one bolt in the outer circle. So the force denoted by p sub 1 equal to area times tau. So therefore, if we try to simply substitute, you have pi. The diameter of the bolt in the outer circle is 10. So pi d squared all over 4 times our uh, allowable shearing stress on the outer circle, which is 60. So this can be equivalent to 1,500 Newton. So that is for the shearing force of one bolt in the outer circle. Then for one bolt, for the second one, for one bolt in the inner circle, so we can have here, we can have the ratio and proportion. So we can have the relationship that P1 all over R sub 1 is equal to P sub 2 all over R sub 2. So this relationship, we have derived this using the Hooke's law. So we have identified here. This is actually for, so that we can, this is actually the shearing force relationship and our radial distances. So for this one, so we can have, we can substitute our P1. So this can be 1,500 pi all over 200, that is the radial distance on the outer circle, which is equivalent to unknown p sub 2 all over 150, the radial distance on the inner circle. So therefore, our p sub 2 is equal to 1,125 pi times n. So that is now the equivalent value for our piece of 2. So from that, we can have now the solution for our torque, which is our unknown. We simply have to sum up uh, the torque for the outer circle and the torque on the inner. So for the torque capacity, if we're going to have now the torque capacity for our given illustrative problem, so that will be T is equal to P sub 1 R sub 1 times N sub 1 plus P sub 2 R sub 2 times N sub 2. So therefore, P1 we have identified a while ago. This is 1,500 pi times 200 times N sub 1, which has the number of bolts on the outer circle, which is 8. Then plus our P sub 2 is 1,125 pi times the radial distance on the inner circle, which is 150 mm, times the number of bolts, which is equivalent to 6. So if we try to simplify this one, this is 3,412,500 pi Newton millimeters. So if we try to simplify further, that can be equivalent to 3.1425 pi kilonewton meters, or this is now equivalent to 10.72 kilonewton meters. So this is the torque capacity for our given problem for this example. For problem number 3, 6, 7 over 8 inches diameter rivets fastened the plate as shown in our figure. So using the result from our previous problem, determine the average shearing stress caused in each rivet by the 14 kips load. What additional load P can be applied before the shearing stress in any rivet exceeds 8,000 psi. Okay, we are given with our figure for problem number 3. We have here the presence of a lateral force, which is 14 kips, and it will produces, or it will create a torque. And we have The second problem is to identify the value for P. So there will be an additional load P in the vertical direction, and of course it will also create a torque capacity. So for this one, for this problem, we try to, it was stated here using the results of problem on the previous problem. Actually, we just have to